Welcome to our webinar on the scale-up and optimization of gas-liquid reactors such as bioprocessing bioreactors or hydrogenation chemical reactors. My name is Nima Yazdanpana. I'm the principal consultant at Prostagence, and together with my colleague Jorge Lopez, who is the senior process design and CFD engineer, going to present the rapid and efficient way of optimization and the scale-up of such unit operations. This webinar is a re-recording of a previous webinar we ran for the Siemens Sim Center in September 7th, 2022. For more information, you can refer to the Siemens webinar webpage shown here and this link. And I'm going to put the link to that page in the description below this video. A quick introduction to the Prostagence, who we are, what we do. Our name, Prostagence, stands for Process Intelligence. We are a consultancy firm helping pharma, biopharma, and fine chemical industries to reduce time to the market, increase R&D efficiency, and reduce R&D spending by mostly modeling and simulation and digital twins. Some savings from our projects we have done over the past 3 years. It depends on the type and size of the projects, and also the metrics. You can see here on the development cost or the time. Our client have had a 60% development cost instead of running experiments, spending time in the lab. Precious material would be used, and instead of that, you could use simulation and the modeling and have the development cost saving or development time instead of running lengthy experiments and manufacturing a scale DOE. So we help them with modeling and simulation and some parametric study through the digital twins, and they would be able to bring the product to market very much faster. Operation cost, you can see on the center, is the yield, is less waste generated, higher throughput, higher productivity, and that's the saving for the future to come, and everyday saving for the rest of the manufacturing process. We have done many projects, many scales, many type of clients, drug substance, drug product, biologic, small molecule, fine chemical, devices. So the spray drying, crystallization, flow chemistry, process development devices, many different type of projects. If you are interested, you can refer to our website or our LinkedIn page, or email us directly at the info@prostagence.com, so we can set up a quick meeting and show you how we work and how we could help you with your projects. For the purpose of this webinar, I'm focusing on bioprocessing and showing you the scale up of this bioprocessing equipments from the lab scale to very large scale manufacturing in a very rapid way. What are the multiphase gas solid liquid reactors? What are the types and applications? In bioprocessing, we have fermentation, for example, in biopharma, wastewater treatments. In chemical synthesis, there are hydrogenation, ozonations, petroleum and refineries, fluid catalytic cracking, Fischer-Tropsch reaction, or in the food industry. So these type of reactors are everywhere at different sizes and designs and applications. However, they are very complex, so the transport phenomena, heat, mass, and momentum or mixing are scale dependent. So we have a gas bubble. In the bioreactor, the gas would be air or oxygen. In hydrogenation, it could be like the hydrogen gas. We have a liquid medium, which would be in the bioprocessing, it would be the bioreactor medium, or in chemical synthesis like hydrogenation, it could be like methanol or the solvent that we are using for the hydrogenation reaction. We would have the solid, such as cells or the catalyst for the hydrogenation, which we would have the mass transfer and the heat transfer. For example, here you can see, you can show some examples from the oxygen transfer from the gas bubbles. Is a flux from the surface area of the gas bubble to the liquid, and diffusing through the liquid, going to the to the solid. If it is going to be cell, diffusing through the cell, going inside the cell, doing all the metabolic activity of the cells, and then secreting the product or the CO2, which then the CO2 should be stripped away by the gas bubbles out to the to the environment. The transport phenomena is at the interface of the gas to liquid and the liquid to solid, and so we would have also the mixing and the medium properties that would change the diffusion properties or the mass transfer, heat transfer, and the dispersion of all the liquids and the nutrients and the gas through the whole system. As an example of the components for the bioreactor or the hydrogenator, so these are typical lab scale or pilot plant or manufacturing scale reactors. So we would have the vessel, so the container. It could be on different sizes and the geometry and the designs. We would have might have different baffles on different sizes and the location. So the mixing elements, which could be like again different size, numbers, angle, types. We would have some probes for the pH, temperature, concentration, different PATs that we need to have in the system to control and monitor the bioreactor or the hydrogenator reactors. Gas supply, mostly through like a sparger. So the sparger would have different type of designs. It could be like a star shape, it could be a ring, it could be perforated plates. Uh, every vendor, they have their own design and they would have all these kind of different advantages and disadvantages. Heat transfer, so through a thermal coil would be like inside the reactor, or like a thermal jacket that would be on the outer layer of the reactor. The continuum of knowledge we need to have from the lab to manufacturing, and is always working hand in hand with the scientist and operator and the technician from the lab and the biologist and the chemist, all the way to manufacturing, to the engineers, to the management. So we are working together on capturing all the knowledge from the chemistry, from the biology, to the equipment, to the plant and the process in a one kind of synchronized way. So the parameter estimation or the knowledge of the chemistry or the biology was mostly defined by the chemist and the biologist. We would have some validation and getting some parameters from the lab scale. For example, how would be the cell behavior at different shear rate, or the metabolic cycle for the cells in the lab scale. Then we go for like a scale up. This is mostly our work, and here showing as again in between the process and optimized process to the lab scale, and so we can design and have some parametric study to find the best scale and the condition that we should run for like optimize space. In terms of scale-up challenges, most of the time or the equipments, or depending on manufacturing or the plants, is very kind of costly and time-consuming. When we sit in the lab scale, so we are working on like the 10 milliliter or up to like 1 liter, 20 liter bioreactors. Here you can see like a small vials all the way to this kind of rocking chair kind of bags. So the processes are long, mostly like 3 weeks. Operation cost is still manageable because we are running at a very small scale. We would have options, multiple options for the different designs and equipments, so we can change the shape of the flasks or the impeller in the lab scale is still affordable to do. However, when we go to manufacturing, now we are talking about 20,000 or 200,000 liter bioreactor. The time is still the same because it's like independent of the scale, so it's it is defined by the cell behavior, but its operation cost is hugely different. We have this huge bioreactor which needs a lot of media, the GMP time, utilities, everything that makes this process very very expensive. And most of the time the equipment is fixed, right? There's existing equipment that we have to retrofit our new chemistry or new biology into this equipment, so we don't have much availability, much degree of freedom of changing different parameter or the design or shape of the bioreactor. So mention about the non-linearity in the scale. When we are moving from the like 100 milliliter to 200,000 liter reactor, you can see the volume is 200,000 liter larger, but the RPM of the mixer or the mixing element couldn't be that much faster. So we even sometimes we go with the slower RPM. For example, in the lab scale, if you're running at 200, 300 RPM, that's something is very high for the manufacturing scale, and because of shaking and vibration and the power you need for the motor. So we normally go for like 100 or like 60 or maximum 200 RPM to have a good mixing and affordable power and the cost. However, the gas rate would be like 100, right? So having a lot of gas causing flooding, causing a lot of also cost for pump around and maintaining the asset utilization for the bioreactor. So you can see this kind of nonlinearity that the volume goes like 200 times larger, but the gas rate is like 100. These are some parameters that we have to explore during the scale up, and the scale up is not a dilation, right? So we don't times everything by 10 or the factor of 100, or we need to capture all these non-linearities by simulations and the modeling, which would be very kind of efficient way to do that instead of running experiment in the lab, which for these kind of large systems and the long processes would be impossible. The work frame we propose here is a digital transformation or like a digital twin. So we start from like ideation in the lab scale and something we can manage through the lab and running multiple experiments in a transient mode. I mean by the simulation, and trying different parameters, different scenarios, different sensitivity analyses, and finding the best condition that would work for our cells. It is a scale in the lab scale, so is affordable and possible to do the validation in the lab scale with like 1 liter, 2 liter bioreactor. And then when we have a confidence on our model is validated, verified, and that's something we can rely on for like a scale up. Then we go for a scale up and optimization of the bioreactor, but just by simulation to like very large scales. Mentioned digital twin, and you might heard this term quite often these years. That's nothing new. This has been around for like almost more than 20 years now. There are different levels of the digital twin. Starting from like the core of the system is like a representation of the chemistry or the biology by equations and the models. Going to like equipment model, that's something we are going to focus today on the bioreactor itself. Then to the process model, then we need to have some one-way data from the SCADA system, or if we want to use this digital twin for the process control, we need to have like a two-way communication of getting the data from the process or the plants, and then overriding the control loops and changing the parameter and have the real digital twin as like a holistic approach to covering everything. So for the purpose of the talk for this webinar, so I'm going to focus more on the just equipment model as a core of the digital twin, and we're going to see what would be the implications here. I mentioned the cell biology, or even the reaction kinetic is the core knowledge we have to capture by our collaboration with our chemists and biologist colleagues. The kinetic model characterizes the systems that include the limits, how the cell behaves, where the high limits, low limits. For example, if we increase the shear rate, very rigorous mixing, for example, are we going to damage the cells? Are we going to rupture the shell and squeezing them and putting them a lot of stress? Or on the lower limit, if we have limited mass transfer or oxygen transfer from the bubble to bubble gas to the liquid to the cells, are we going to have a starvation? The cells cannot breathe very well, and they cannot go through the optimized biologic cycles, and then some of them would die, or they go to, instead of aerobic process, they go to like fermentation process. So there are like low limits and the high limits that we define our design space. And then if we are staying on the center of these, on like kind of balancing everything, it would be the healthiest and the most happy condition for our cells, or even for biochemistry. Here's a balance of equipment characterization and biologic system requirements. So that's something we have to define from the beginning, and always put as a goal to maintain that criteria or the threshold, that we are not damaging our cells, or providing them enough nutrient and the oxygen at a good rate. Now we're getting to the simulation and the modeling of the transport phenomena at the interface and through the liquids. There are different parameters that impacting these transport phenomena. At the interface of the gas and liquid, we would have the shear and the mixing impact, the medium impact, and then the sparger. How is the design of the equipment, the working volume, impeller design, and on the medium side we would have like the pH, the property of the liquid, temperature, dissolved oxygen saturation level, and those kind of information. On the sparger, how is the design of the sparger, how are we going to make the bubbles, what the number of the bubbles we are making, and the sizes. And as you know, the mass transfer for like a smaller bubbles would be faster, and a higher rate is a flux, is a mass transfer per surface area. So when we have a smaller bubbles and the more number of them, we would have the overall higher mass transfer rate. Through the liquid, by mixing, we would have the vessel design, medium, and the shear design, impacts. On the medium, it could be like viscosity and the density of the liquid. For the shear rate and the mixing, what is the RPM of the impeller, the working volume of how much liquid we have in the vessel, energy dissipation and the diffusivity. And then we're going to like the vessel design, number of the baffles, types, and working volume, geometry of the vessel. Is it a tall and skinny, or is it short and chubby vessel? So it would have all impacting on the energy dissipation and the diffusion length that would impact the mass transfer and the diffusivities. At the liquid to solid mass transfer level, so we would have the cell biology with from the omics to oxygen uptake rates, size and dispersions of the cells through the liquid. On the medium, on the liquid, so we would have again density and viscosity, saturation level of the oxygen or the CO2. What's the impact of shear, the mass transfer bond layer, and the working volume that would be defined by the mixer. These are all interconnected and impacting each other. For example, you can see here the mixing is repeating almost everywhere for all these three steps. And we would need to solve all these equations and running the simulations in a synchronized way, considering all the parameters, all the equations, and all the transport phenomena at the different stages and different level. This sounds easy, but is actually very kind of complicated when you're going through the simulations, starting from the parameter estimation. Important information to capture from the chemistry or the biology is the cell behavior, the system biology, how the system behaves, the different shear, different temperature, different pH. These parameters are not easy to capture, and the biologists and chemists, they have their own way to have some parameter estimation for those kind of core equation that we have to put into the simulations. Equipment blueprint, the CAD design, or some geometry and measurements is easier to obtain when we're working with the clients. If is a new design or relatively new design, they would have some engineering blueprint that they could send to us, or we just need to have some measurements with like measuring tape and one operator. Sometimes when the reactor is open, they could do the measurement and do that like a hand drawing for us. Then we can convert it to the CAD for the simulations in our simulation systems. Computational resources on our side, could become very expensive when we are running a multi-parametric study with the high fidelity simulations. So we have to go to high performance computers, HPCs, to the cloud. We're getting a lot of CPUs or GPUs to run these expensive simulation and for multiple days. Model setup and solver selection, and which also alluded to the verification and validation, is another critical steps. Is not all the default equation in the simulation that we can use. Every time we need to pay a lot of attention to the type of system. Is it aqueous phase? Is it like organic solvent? How is the diffusion? Where is the diffusion model? The KLA, all these equations that we have to set up manually and do some coding in the background. Is paying more attention to these steps pays off at the later stage. Setting up the correct tools and the boundary conditions and the equations and the parameters is very important. Verification and validations is the last critical steps and it's also complex step. All these simulation could be colorful and sexy and shiny, but all could be wrong, right? So if we don't set up the right models, don't select the best solver, then it could be giving us some wrong results. So we have our own internal SOPs for verification and the validation of our codes and the calibration of the parameters. We would need to run a couple of models, initially to get the parameters, to get the error, check everything working fine. So we use different kind of mathematical methodologies to verify our models and the simulations first. Then with the validation, we do validation with the experimental data in the lab scale. Jorge is going to show our workflow here, how it works, and then we could get the validated simulation. We could be implemented into the industrial scale applications. And now I'm handing over to Jorge to present the bioreactor scale-up. This was an industrial scale bioreactor, and he's going to show from the simulation side all the way to the application and optimization of the bioreactor.
Thank you, Nima. So I'm going to be talking about the actual case study of the bioreactor scale-up. So this is the project that we were working on. So we started from a bioreactor in a lab scale of 100 milliliter, and we wanted to scale it up into a manufacturer scale of 20,000 liters. Here you have for your reference the dimensions and the characteristics of each of the two scales. But before we jump into the actual results and see how we did the scale up, we want to talk a little bit about the mass transfer and the modeling of the microorganisms. So when we talk about mass transfer from oxygen to liquid, we included the model of the oxygen mass transfer by dissolution, and the dissolution is driven by this equation right here. And if you see this equation in a graphical way, this is what you get, which is basically the change of the concentration of oxygen in time, and how fast it reached to how fast the concentration of liquid reached to a saturation is basically the KLA. The higher the KLA, the faster you're gonna get to that saturation level. Now, when we take a closer look into the equation, we see that it depends on a few different important parameters. The first one is the A, which is basically the area for mass transfer, which is related to the bubble size and to the number of bubbles. The second one is the saturation oxygen level, which is related to the dissolved oxygen, the medium saturation at that particular condition, and what is the oxygen uptake rate, basically how much oxygen our microorganisms are uptaking for their metabolism. and the OTR, which is basically how fast are we transferring the oxygen from the gas phase into the liquid phase. Now the concentration level is provided as is the equilibrium oxygen concentration, and we can obtain that from Henry's law coupled with the oxygen uptake rate. But what we want to find and what we want to optimize is the KLA, basically the mass transfer coefficient. And there is two ways of calculating the KLA. The first one is basically from the experimental data solving this equation right here. So if you have experimental data that look like this, you measure the concentration of oxygen in the liquid in time, you can then solve this equation to get the KLA as the slope of the straight line. The other way that you can calculate the KLAs is using some dimensionless parameters, for example, the Sherwood number. So that's the modeling configuration from the mass transfer from the gas and liquid. But if we talk now about the microorganism modeling, we need to take a few considerations. The first one is that we need to define what is the oxygen uptake rate of the biosystem that we have in our reactor. And here you have some specific OUR for different bioorganisms, bacteria, yeast, or molds. Now this is going to be dependent on a viable cell density that you want to have or you currently have in your bioreactor. And we're going to see how this looks in the results of the optimization later in the slides. The second thing that you need to take into account is the environmental stress that we are inputting into the organisms. Because we have a mixing element, we're going to have some environmental stress driven by the impeller, and it's going to be affecting the health and the metabolism of the microorganism. And you also need to consider the pH, the temperature change, all of this in the omics of the microorganisms. So we took all of that and we built a CFD simulation to solve this issue. And the workflow of this simulation we divided into three different steps. So step one was basically simulate the actual case that we have in the lab scale where we have some experimental data for validation. So we build these steps and we start with this step because that's the way that we can validate our CFD model with the experimental data that we have. It allows us to fit and to estimate some parameters needed in the simulation and to express the cell behavior limits. So this simulation that we built up for this step was it was a transient simulation because we had the data of the dissolved oxygen in time, and the simulation that we run was from the lab scale bioreactor. We did a symmetry, or we simulated half the bioreactor because the tank was symmetric. Now step two, we still are in the lab scale, but we want to convert the transient simulation into a steady state simulation. The reason why we wanted to do this is to save computational resources, because a transient simulation is a really time consuming type of simulation. So if we could, instead of running a transient, run a steady state model, it's going to be way faster, and we can, when we do the scale up, it's going to be much faster and easier for us. And then we're going to validate the steady state simulation with the transient simulation and with the experimental data, and that's going to be our base case scenario for the scale up and for the manufacture scale. So this was the same setup of simulation from the previous step in the workflow, but we just changed the transient and the state up, and we transient to a steady state, and we compare the KLA. Then the last step in the workflow was to do the actual scale up and to test and to simulate the manufacture scale. So the first thing that we did was to run a virtual DOE. So we want to explore the limits on the operation of the bioreactor in the manufacture scale, and then we did an optimization to find what was the optimal condition to run that bioreactor to maximize the KLA. Then we compile those results from the virtual DOE and the optimization to create a process digital twin. And then we could take that to explore the sign space, to explore the parameter acceptable range, the normal operating range, and the CMC. Now this simulation was a steady state simulation because we already validated that in the previous step in the workflow. And we did a parametric sweep for the VDOE and optimization study for the optimization, and we run these to the DOE and optimization in an HPC. Now let's jump into the actual experiment results. So this is an example of one of the experimental results that we had for this case. So you have the measurement of the dissolved oxygen in the liquid in time, and then solving the equation of the dissolution, you can calculate the KLA by the slope of the straight line here in the measurement. And we did exactly the same thing in the CFD simulation. We measured the concentration of oxygen in time, we convert the results into a straight line, and we calculate the KLA. You have here the value for the experimental and here for the simulation. So overall, we have a similar mass transfer rate. We have a couple of differences, and those differences might be attributed to, first, an error in the experimental measurement of the dissolved oxygen, and second, an overshoot in the mass transfer in the CFD code due to the bubble size distribution. So remember that I told you that we had to fit some parameters for the bubble size distribution. That error may be coming from that fitting process, but the overall error is less than 10%, which is pretty acceptable. Now that's step one in the workflow. Step two is that we run the same case in a steady state, and we extract the KLA, and you can see here the results, the KLA from the steady state simulation. And what you can see is that we actually have a lower error in the KLA prediction from the steady state compared to the experimental. So this gives us confidence that the model that we set up in the steady state was going to be accurate in the scale-up process. So when we talk about the scale-up, the first thing that we did was a parametric study or a virtual DOE. So for the virtual DOE, we chose three variables to study. The first one is the VVM, or how much gas are we injecting into the system, the volume of sparge air. We tested 7 intervals from 0.01 to 0.1. We also changed the impeller speed, the rotational speed, 7 intervals from 20 to 80 RPM, and 3 different impeller configurations. So we have a configuration where we only have Rushton turbines, and 2 configuration where we have a combination of elephant ear and Rushton turbines pumping downward. Now the reason that we chose these 3 parameters is because this is a brownfield project. Basically the bioreactor already exists, meaning that we cannot change any of the geometric characteristics of the bioreactor. The length, the diameter, the number of baffles, the sparger, it's all fixed. These 3 parameters are parameters that we can change in the operation of the bioreactor. The VVM or the RPM is independent of the bioreactor itself. And we were lucky enough that the client had the ability to change the location of the impeller and the configuration of the impeller by just screwing them up and down the shaft. So that's why we also chose these 3 configurations of the impeller as the study parameters. So for the virtual DOE, we run 147 simulation, which is the combination of all of the combination of the 3 parameters, and we run the simulation in the Siemens HPC with a total runtime of 36 hours. Now these are the results of the virtual DOE. So all of the results that I'm going to be showing here are in the same format, where we have here a variable of interest, in this case is KLA, as a function of shear rate for the 3 different impellers, each represented by 1 color, and different VVM represented by a bubble size in the plot. So the color blue represents the impeller 1, which is all Rushton turbines. Impeller 2 is the green one, which is the first combination, and impeller 3 is the purple one with the second configuration. So from this plot, what you can see is that the higher the shear, the higher the KLA, right? Now this makes sense because higher shear rate leads to higher bubble breakup. As we break up the bubble, we're going to have smaller bubbles and a larger number of bubbles, increasing the mass transfer flux. And if you remember the dissolution equation, the area is a key parameter in the mass transfer. So the higher the bubbles and the smaller the bubbles are, we have a higher surface for mass transfer. Another thing that we can observe is the higher the VVM, meaning the higher the bubbles in the plot, the higher the KLA. And this also makes sense. The more gas we inject into a system, more mass transfer we have. Now this slide in here is, instead of evaluating the mass transfer, we want to see the effect on the shear rate and the dissolved oxygen. So here in the left you have the shear rate as a function of VVM, impeller configuration, and RPM. And from this plot you can see a few interesting things. The first thing is that the higher the RPM, the higher the shear. So the bigger the bubble in the plot, the bigger the shear rate. This makes sense, of course. But an interesting thing is that as we increase the VVM from left to right, we don't see a significant effect on the shear. But what we can see is that if you focus here on the upper section of the plot, impeller 1 has a higher shear rate compared to impeller 2 and compared to impeller 3. And this is going to be important in the next slide when we talk about the bubbles distribution. And when we talk about the dissolved oxygen, you see that impeller 1 and 3 has a higher level of dissolved oxygen compared to impeller 2, and this is also related to the bubble size and the bubble residence time. Now in here we're gonna see the effect of the impeller in the gas phase dispersion. So here you have the results of the bubble size, the mean diameter of the bubble, for the 3 different impellers for the same RPM and the same VVM, right? And now, just before we jump into the result, I want just to clarify that a Russian impeller is a high shear impeller, which leads to a high bubble breakage, and it is characterized by a radial flow. And the elephant ear is a low shear impeller, which has an axial flow. So with this in mind, we can just start looking at the results. So we have here impeller 1. So since this is the one with the 4 rostron, this is the impeller with the higher shear rate, and we saw that in the previous slide. Now you see here the high bubble breakage near the impeller, because this is the area of high shear. You see how the bubble size goes down in the image, but the radial flow profile by the impeller leads to low bubble residence time. Now impeller 2, you have here the combination of the two impellers. So when the bubbles are injected here at the bottom of the sparger, the first elephant ear is pushing the bubbles downward, but not breaking up the bubbles. The bubbles are braked just when they reach the first rostron impeller. So we have not an adequate bubble breakage in this system. Impeller 3, on the other hand, when the bubbles are injected into the system, they are broken down by the first rostron impeller, and then the first elephant ear pushed down the bubbles, enhancing the bubble breakup of the first impeller. So we have now here a high region of smaller bubbles and a higher concentration of bubbles, which lead to a higher KLA. Now the downward flow of these two impellers, the elephant ear, are increasing the bubble residence time, which is also increasing the mass transfer for that particular configuration. But from this virtual DOE, what we wanted was to explore the limits of the design space. So in theory, you can run the bioreactor in any specific configuration that you want. You can run at any RPM, at any VVM in theory, but in reality you have some limits on where you can operate the bioreactor, and this is what we obtain doing this virtual DOE. For example, if you operate the bioreactor in this region here, you're going to have cell starvation. Basically, you're not going to have enough mass transfer for the bioreactor for the biologic performance. So you're going to have insufficient OTR for the OUR that you have. If you operate the bioreactor in this region, you're going to have a high shear region, or a high shear in the bioreactor, which is going to damage your cells. And we can define a threshold of what is the maximum shear rate that we can get in the bioreactor for the operation of the of the reactor itself. And if you operate in this region in here, you have a higher power consumption because you have higher RPM, meaning higher electricity in the electromotor. You have higher gas compressor and conditioning of the gas. So this is unfeasible from an operating point of view because it is a high power consumption. So we can create this region here when we can operate the bioreactor, and now we want to find what is the optimal condition to run within those limits. And this is what we did by setting up the optimization study. So the goal was to maximize the KLA. And we have some constraint, and the constraint is the average heat rate as we saw in the previous slide. Now, what we want to get is the optimum condition, basically what is the best combination of all of the tested parameters. But we also want to find the local optimum, which is basically what is the next base in case we cannot run the global optimum because we have some equipment process or any limits or change. So we kept the three study parameters, VVM, RPM, and the impeller configuration within those limits that we defined in the previous slide. And we run an optimization study where we tested 200 different combinations using the Sherpa algorithm for the optimization in a Siemens HPC with a runtime of 72 hours. And this is basically the history of the optimization study that we conducted. We can each point in the graph represent to one simulation that we tested, and they can be either feasible or unfeasible. Feasible meaning that they satisfy the condition, the constraint that we set, and unfeasible they don't satisfy the constraint, and we found a global optimum and local optimums. Now, when you run this type of optimization study, you can create these types of optimization dashboard, which is a visual way of understanding your optimization study. You can combine plot, widget, different tools to have a tool to make informed decisions. But what I want you to take a closer look is this plot here on the lower left, which is a correlation plot. And in there we can see different correlation of variables and responses in our system. So we can see some apparent correlations, something that we already know beforehand, which is the effect, the correlation between RPM and the power, or the RPM in the shear rate. The higher the RPM, the higher the power consumption, the higher the RPM, the higher shear rate. But we can find some additional correlation that we may not be aware of them before we start setting up this study. For example, the effect correlation between RPM and mean diameter of the bubble, shear rate and KLA, and shear rate and OTR. So with this type of study, optimization studies, and using this dashboard, you can create a knowledge of the operation of the bioreactor because you are finding correlation of variables that you may not know beforehand. Now, all of the results that I have shown to you here are from the mass transfer from the gas to the liquid, but we haven't talked about the modeling of the microorganism and the cell biology. So remember that when we talk about the modeling, we have a balance between OTR, basically how much gas are we providing how much oxygen are we provided by the gas, and the OUR, which is how much are we consuming, how much the cells are consuming. So for this biologic system that we had, the specific OUR was around 12 millimole of oxygen per gram per hour. And for the viable cell density that we had in this case, the OUR was around 1.25 to the power of minus 7 kilogram of oxygen per meter cubic second, which is this line here. Now, this plot is telling you in all of the tested cases that we had, what was the OTR, basically how much gas will we provided in the mass transfer from the gas to the liquid, and we have the balance between OTR and OUR. So if a simulation or a case, you have an OTR which is less than the OUR limit, basically you are in this region in here, you're going to have cell starvation. You're not providing enough oxygen into the liquid for the proper cell biology. So you're going to have cell starvation, your concentration of cells is going to decrease, and since this is a cell-regulated biosystem, you're going to have a new cell density and a new OUR. Basically, you're going to lower this limit until what you can provide, and you're going to lower that limit because it's regulated. But if your case you have an OTR higher than the OUR, you have sufficient dissolved oxygen for the cell metabolism, so you're going to have a proper cell performance. This case in here, this star in here, is the case that we found that was our global optimum, where the OTR was higher than the OUR, so we know for a fact that we're going to have sufficient DO for the cell metabolism. And here you have just the description of what was the base scenario that we found. So we found that the global optimum was a case with the impeller number 3, which makes sense because what we saw about the combination of the Russian and elephant ear in the bubble size distribution, residence time, and mass transfer. And these are the RPM and BVM that we found to be the optimum. But not only the additional benefits of an optimization study is not just to find what is the best case and the best condition to run your bioreactor. We're basically creating a lifetime value of the process knowledge, because we are finding variable correlations that we may not know beforehand, and we're finding global optimum and the best designs that we can test and run. And doing this, we can increase the yield, the throughput, and the profitability by lowering and reducing the operating cost, the downtime, the cycle time. We can create this type of plots here on the right, where you can map where are your feasible and your non-feasible designs, and you can find this and create a neighbor of your near or your neighbor of the best design, which is telling you what design to run if the global optimum is not possible. It's also telling you what designs not to run because they are not feasible, so you don't have to waste your material and time running these conditions which you know they're not going to be feasible. So you're building that process knowledge, not just finding the optimum condition. And we can keep extending this benefit by compiling all of these results of the model of the equipment and create a digital twin of the core model. And we can do this by creating a surrogate model. So basically a surrogate model is creating a digital twin of your unit operation, which you can couple with the digital twin of your virtual plant. And the good thing is that by doing this digital twin and this compiling of the results, you're creating a lifetime equipment model that you can use for a quick evaluation of the system performance, you can use for advanced process control, and you can plug in these tools in different codes, so you can couple live data control optimization into a physical plant digital twin. But we're not going to go too deep into this topic, but you have to be in the lookout for a future webinar that we're going to be talking about the plant-wide digital twin and how this model of a unit operation couples with the whole digital twin of the plant. And this concludes this seminar. I want to just give a special acknowledgement to the Siemens team for the technical support. And do not hesitate to contact us if you have any questions or comment, and also don't forget to check out our LinkedIn for any updates and future news. Thank you.